Kia ora and welcome. This is the third of a mini-series of 4 webinars to showcase some of the recent developments in remote sensing technologies and how these are applied to answer questions for policymakers, councils and landowners. Today we're talking about deep learning, which enables imagery to be analysed quickly and efficiently to extract valuable data. However, data sets, whatever their sources, are rarely complete or perfect. Brent Martin will show how deep learning's ability to train on imperfect data was harnessed to overcome those limitations and achieve some good results. Brent is a senior data scientist at Manaaki Whenua and works with many large and fascinating data sets. In over 30 years as a machine learning and AI specialist, Brent's career includes a decade of lecturing in computer science at Canterbury University and a stint at Google in New York using machine learning to help avoid embarrassing search engine bloopers. I know that you're going to have lots of questions and just ask that you put those questions into the chat box as early as you can so that we can get organised for the Q&A session at the end. Over to you, Brent.
Thank you, Christine. So good morning, everyone, and thank you for joining me for this talk. What I'm going to be doing is talking a bit about how we are diving into the area of deep learning for dealing with spatial data at Manaaki Whenua. And in particular, we're going to jump into a particular project which was looking at historic aerial imagery. And this is to get a bit of an idea of both the promise and the challenges that deep learning presents to us. This is a project that's been a collaboration of a fairly large number of people. It's multidisciplinary. So I thank all those people whose names are on the slide. So we all know these days that the amount of data we have available to us, and this includes imagery, is just growing exponentially. And this could be both a challenge or an opportunity. The challenge, of course, is how do we deal with these massive amounts of data? If we try to do things the way we've always been doing them, is it even possible for us to process all of the data and imagery coming in and to make use of it? The opportunity, on the other hand, is that with the amount of data and especially the periodicity of the data and imagery available now, we have the opportunity to pull out insights that we've never been able to do before, such as seeing trends over time in imagery and mapping those changes. So at Manaaki Whenua, we've been getting involved in the last few years quite heavily in computer vision, not only in remote sensing, but in other areas as well. And this is very much around deep learning. So some of the examples of the sorts of things we've been experimenting with, we've been looking at whether you can classify species from imagery. In the example at the top, those are beach pollens, and can we tell one species from another? Can we detect predators in trail camera imagery so that people don't have to troll 500,000 images looking for the stoat? In the case of remote sensing, can we segment land into the types of layers we're interested in, such as land cover, land use, landslide susceptibility, those kinds of things? And finally, if we want to get really ambitious, could we start putting all this together, adding some extra AI and using it to make things such as drone flights autonomous? So for those who haven't been involved with deep learning before, this is just a really quick introduction. Deep learning is a machine learning approach mainly, and it's been around for about a decade now, and it completely revolutionized the area of computer vision. So back before deep learning, computer vision had a lot of machine learning in it, but what typically happened was you had images, you had training labels that said what was in it, and then you had humans who would extract features from the images that were thought to be predictive. You'd then put them into a machine learning classifier and it would learn how to discern what was in an image. Deep learning changed all of that by taking out that human component, because what deep learning promises to do is to take the images as they are and to actually learn all of that feature extraction as well as the final classification. How it does it is that deep learning is a network which consists of a set of subnetworks that learn increasingly complex patterns, starting from very, very simple shapes and working their way up to, for example, individual human faces that can be recognized. So how does this apply to remote sensing? Well, one of the things that we can do with deep learning is something called segmentation. And the way that segmentation works is we take our imagery and the labels, which might be the land cover class, we use them to train a deep learning algorithm. And what we can do then is we can do things like we can infer what the deep learning model believes the land cover is, compare it to something we've done by hand, such as the Manaaki Whenua land cover database, look at the differences and decide whether those differences are real, whether they are trends over time, and so forth. Another example we've been experimenting with is in the area of forest destocking. This is a partially manual, partially automatic process where humans have to take the automatically detected potential forest destocks and decide whether that's really what they are or whether they're a cloud passing over the image or a road somebody bulldozed through or whatever. We can also train the deep learning network to do that job for the human. A different way of applying deep learning to remote sensing is object detection. The image you can see in front of you is from a large collaborative project that we're doing with Singapore and various other organisations around New Zealand. And this is led by Manaaki Whenua's Jan Schindler, and he produced this map using deep learning. And what it's done is it has learned how to segment the individual trees in the urban landscape. And what we can see here is a bit of the Wellington foreshore with those individual trees having been picked out by the deep learning model. So let's take a look at the project of interest today. This project is about how can we map the urban built form over time so that we can see changes in it. And this is a really good example of not only the promise of deep learning, but also one of its challenges. So what we want to be able to do is we want to come up with the footprint of the buildings from 1940, 1980, and 2016 for, in this case, 3 cities. And what we want is those masks at the bottom, so we can look at that and get some insight into what's been happening to the built form. The challenge is that in 1940 and 1980, the only imagery we have available has been scanned from old black and white images. So we'll use that deep learning segmentation approach. What we can do is we can take a bunch of images, we can take the labeling, which in this case is the building outlines, feed those in pairs into a pipeline that we've created, which chops them up so that they can be fed into the deep learning, feeds those into the deep learning encoder decoder in pairs of images and labels, and it learns how to output a mask that represents the buildings. We use the National eScience Infrastructure, or NESI infrastructure, to give us our compute power, because that's a platform for very high compute, which is needed for this training. It's very compute intensive. So how do we do this? So first of all, for the current period, we can do this quite simply. The training data to label where the buildings are can be obtained from LINS. They've got a layer called the New Zealand Building Outlines, and that layer was extracted from 2016 aerial imagery at 0.3 meter resolution. So we can get both the labeling and the imagery from LINS, and we've got a perfect match for our training data. It gets a little more interesting though when we go into the past. So for the historic imagery, there is a website called Retrolens, which catalogues all of the aerial imagery that's been taken over New Zealand going right back to as early as the 1920s. So we can use Retrolens to find the images we want for the period we want, and you can download images directly from Retrolens, but their quality is not very good. So we go back to LINS, give them a huge list of images and get them to give us those images, which we then have to mosaic into a single mosaic for each city. So the big challenge we've got is how do we train a model that is going to do all this for us? We've got the 2016 labeling data and imagery, but the question is, first of all, if we train a model on 2016 data, will it work for 1940s and 1980 black and white imagery, which is what we're really interested in? And secondly, ideally, we'd like to be able to train on a few cities and then apply it right across New Zealand. That would be fantastic, but does it work? So first of all, that question about transferring between time periods. Can we use 2016 modeling to find the buildings in the 1940s and 1980s? Unfortunately, the answer turns out to be no. So on the left, we can see the buildings that have been picked up in a 2016 image, which has been made grayscale, and we can see that it does a beautiful job of picking out the buildings. We then go to 1940, we look at that image ourselves and it doesn't seem too bad, but in practice, the model performs extremely poorly on that and only picks up a very small number of the buildings. So what's the problem? Well, the problem is really the inconsistency in the images, their characteristics and quality. In 2016, we've got digital imagery. It's highly standardized in terms of brightness and contrast. It's very, very clean with minimal noise. It's in sharp focus, and the spatial accuracy with that labeling data is extremely high. The only issue that we have with the 2016 imagery is that long shadows can obscure parts of buildings, but in practice, it's not a big deal. We go to 1980 and the scanned photography, the black and white photography, and everything changes. First of all, the contrast is quite different. Generally in 1980, it was very flat. The main problem though is the fact that the images are grainy because they're old film images. And that grain is not just obscuring detail, it's introducing patterns that the model has never seen before. And you could imagine, for example, that graininess looks just a little bit like the texture of a tree. So it might determine that most of what's in this image is in fact vegetation. The focus is also not as good. The spatial accuracy varies from good to poor, and that's because the historic imagery for 1980 is somewhat distorted, and even the best techniques today have difficulty in dealing with all of that distortion. The only good news about the 1980 film is the fact that the shadows are nice and short, so we don't have that obscuring problem. Then we go to 1940 and everything's bad now. The brightness and contrast is hugely variable. The graininess is worse. The focus varies from not too bad to absolutely dreadful and so on. And that spatial distortion becomes much more acute in that old imagery. So what can we do? Essentially what we have to do is we have to introduce training data for the historic imagery, but we don't have it. So what we thought we would try out is, could we use the current labeling, in other words, where buildings are now, but use imagery from 1940 and 1980? And the problems are obvious here. The first one is a lot of the buildings weren't built in 1940 and 1980. And we can see an example in the bottom right of this image, circled, showing some buildings that didn't exist when the photo was taken. And they also may have been changed, they could have been demolished and so forth. The other issue that we have is that one of the displacement. So because of the distortion in the imagery, we can see, for example, in the sort of middle of the left of the screen here, that we've got buildings here that existed in when this photo was taken, but they're just a bit displaced in the image. It looks like by maybe a couple of meters, and that's because of that distortion. And what that does is it means our labeling has got another layer of noise where it doesn't quite match up with the imagery. Nonetheless, we give this a try. And what we do is we just look through all of those tiles. So we've taken the mosaic, we've broken it into lots and lots of little tiles, and we just choose the ones that we think is a good enough match. And the question is, what's good enough? Because in deep learning, it's extremely important to have enough imagery, because if you don't have enough imagery, it will tend to overfit to what you trained it on, and then it doesn't predict very well. So in the end, it was kind of a gut feel. We need to get enough images, but they need to be good enough. And although this image I'm showing you here might look like that labeling's not that good, actually this one I would say was good enough. There's enough overlap between the buildings and the labels for it to work. We think an approach like that would work at all. Well, because we've seen it before. So here's a couple of examples from the tree segmentation work we've been doing. On the left, we've got images of some forest in Chile, and the polygons, the red polygons, are Pinus radiata. At the top left, we can see a scene there, and on the right, we've got what was predicted. So the colors in this imagery are telling us the yellow means it's correct, and the blue means correct and not pine. The red means we missed something, and the green means we predicted pine when the labeling says it isn't. So it looks quite noisy, but if we look at the example that's got the circle around it here, and that's it blown up on the bottom left, what we see is that for whatever reason, whoever labeled that tree didn't do a particularly good job of it. However, when we look on the right-hand side at what we predicted with our model, the combination of yellow and green is the tree outline that we predicted, and you can actually see that that's a considerably better outline than the one that the training label had. So in other words, if we take imperfect training data and train a model, it learns to ignore the pieces of the training data that don't have any visual support for them, and actually comes up with a model that works better than the training data. On the right-hand side, we have a similar thing in object detection, where problems such as false positives in the labeling get removed after we train our model and rerun it on that data. So, did that all work for the buildings then? We've taken this imperfect data training sets and we've trained up models for 1940 and 1980. So here's an example for 1940. And on the left, we've got the image. Doesn't look too bad, but in the middle, we've got what the model trained on 2016 data alone produced, which is terrible. On the right, we've got the result of our model using that imperfect data. And we can see that although the shapes of the buildings is a little bit kind of odd, a little bit blurry, the footprint that it has picked up is a much, much closer representation of the buildings in that image. So that's worked pretty well. For 1980, the problem wasn't as bad in the first place. And in fact, if we look at the 2016 mask on the surface, it looks really good. But when we look closely, we see that there are buildings, including this great big building here, that are almost entirely missing. When we now use that imperfect data and train up a 1980 model again, voila, that building reappears. And in fact, if you start looking closely, you'll see there are actually lots of buildings missing from the middle mask that all reappear. So again, it's worked really well. We're again seeing that slight blurring of the shapes. That's caused by that displacement problem. The fact that the labeling and the imagery didn't quite line up means the edges of buildings to the model become a little bit ambiguous, and that's why it doesn't quite do as good a job at getting an exact footprint. But for our purpose of measuring the building footprint, it's an excellent result. And finally, can we transfer between different cities? So we took the lazy step of not bothering to do any modeling for Auckland at all, and instead we applied the Wellington model. And what we see here is that for both 1980 and 1940, the Wellington model does an excellent job of picking out the buildings in Auckland. So having done all of that, we now have a system that works well, even though at the beginning it seemed like we didn't have any training data. So what do we get out of it? Well, so here's a few examples of our three cities. For Hamilton, we can see from the mask that the model has generated the obvious, that Hamilton has grown spectacularly between 1940 and 2016. But also we can see how the buildings have changed. We can see on the left in 1940 how the building density was low, especially over here in Hamilton East. And then we go to 1980, we see it densifying, and we also see the city increasingly starting to industrialize and commercialize. And then when we get to 2016, we see that whole process of densification and commercialization really ramping up. Auckland, we see a similar thing. So looking at downtown Auckland here, we see the, it being extending and industrializing on its margin, and we can see that densification quite clearly, how the image is becoming more densely populated with the white buildings, particularly between 1980 and 2016 as infill housing is really ramping up in Auckland. And then finally for Wellington, Wellington's the surprise one. When we look at the top images there, which is sort of the central city area, although we can see it commercializing to some degree and intensifying, it's nowhere near the same as the other two. So in fact, Wellington's, this main city, hasn't actually changed that much apart from growing since 1940. On the other hand, if we look at Lower Hutt as a comparison, we can see how that densification and commercialization is much, much more obvious in that area. So to summarize then, we had a problem we needed to solve where we wanted to be able to extract those building footprints from historic imagery. We have the problem that always comes up with deep learning, that the biggest challenge and the biggest cost is acquiring training data. But in this case, we showed that by learning from imperfect data, some of these problems that we might want to apply deep learning to that seem impossible can become possible by using that approach. And as a result of that, we can gain insight into data that we might not have thought possible before, and hence deep learning has great potential for the taming of that data deluge and being able to present us with new innovation and new knowledge out of the data that we have available. Thank you, and I'll take questions.
Great. Thanks very much for that, Brent. That was really, really fascinating. I always wondered what happened under the bonnet, and that's been a great insight for us. I've got a quick question first. Deep learning is usually used for images. What else can it be used for?
So although deep learning is associated with imagery and particularly sort of standard color photography and things like that, it can actually be used for anything where the data is spatial in nature. So if your data is something that can be represented in 2 dimensions or 3 dimensions and that makes sense, then deep learning is able to find patterns in that which it can use for prediction. The other thing is we can also layer more than one thing on top of each other. So we might take more than one image, for example, multiple points in time, stack those together and present them, and the model will now learn to detect change rather than learning to to identify classes or something like that. And we can also take imagery and other spatial data such as other layers. We might have a soil layer that might be relevant to what we're trying to do. We might have an elevation layer. We can put all that sort of data together as well, and out of that we can train the model to detect what we want.
Great, thank you. Carl has asked, do you think you'll be able to classify the type of building, such as dwellings, using these techniques?
I see no reason why that wouldn't be possible. It would be interesting. I guess the issue, if we're thinking about modern day, that might not be too difficult in terms of information we might have about the buildings. As we go further into the past, it might get a bit more interesting. We could, for example, if we're looking at the sort of urban development, in the modern day, we have the district plans, for example. So we've got, at least at a course level, this area is residential, so those should be residential dwellings and so forth. So again, we might be able to use that. That might be good enough to train a model to detect, hey, I think that's a residential building and I think that's a commercial building.
Great. And now a question about the balance of human input versus the machine learning.
Yep.
Joe was questioning whether, there's still quite a lot of human input into the training data set. And so, is it really just that we have more training data, or is the deep learning really carrying the load itself?
So that's a bit of a movable feast, and it partly depends on the problem you're trying to solve and the other data you have available. Just by way of example, at the beginning of the talk, I showed you that image of the trees in Wellington and the model that had been trained to pick up the individual tree crowns. The training data that was used for that was entirely automated. So prior to using deep learning, we've been using another approach, which is, if you have LiDAR available, you can use the LiDAR to get to compute a canopy height model, and that canopy height model can then be, you can basically extract, just from looking at the topology of it, you can extract where you believe the trees are. So that was the training data used. There was no human input involved in that at all, and that was that imperfect data again, and that gave us the ability to train a model that did a better job of picking the trees up. On the other hand, it's not perfect, and what you can do is you can use an approach called infusion, where you do as much automated use as much automated training data as you possibly can, and then you maybe just for a relatively small subset of data, you produce very, very accurate human produced training data. You put the two together and that can give you a better result than what you started with.
Fantastic, great. Here's one close to our hearts at Manaaki Whenua. Do you think deep learning would be useful for mapping or detecting wetlands that often have multiple land cover types, such as water, vegetation, or bare soil?
Yes, I believe they would. Again, the issue with this one will be putting together some training data to make that able to happen. Wetlands is a really good example of where we probably wouldn't just use an image, but we would use a stack of images and potentially other information as well, including an elevation model. If we've got areas where we've got super accurate LiDAR, we could use that as well. But generally speaking, that we would at the very least be using a time series of imagery, and the deep learning should be able to detect not only what a wetland looks like, but also how it changes over time. And with respect to the fact that there are different appearances to a wetland, that shouldn't be a problem because these models have huge capacity. So in other words, they can learn a lot of different concepts at the same time. So although we might just be trying to get an output of wetland or not wetland, under the hood, there may be representations within the model of a wetland that is fully vegetated, a wetland with a completely different type of vegetation and so forth. Or alternatively, we could directly tell the model to differentiate those things, and then we can aggregate at the other end. If it thought it was a vegetated wetland or whatever, we can just bring it all together to say, yes, that's a wetland in that spot.
Great. We've got a few more questions. I'm just going to finish up with one slightly technical one, and then rest assured everyone else who is putting questions in, continue to do so, and we will come back to you directly and share the questions along with the other presentation material. But Robert has asked about some of the technologies that are used for restoring old family photos, and I believe there's something called graph neural networks that is used to improve and generate better photos from old ones. Have you considered using that?
We didn't. So I'm not familiar with that exact technology that you're talking about, but I am familiar, for example, with there is technology out there now that is used commercially by people such as the satellite image provider Maxar for essentially improving the resolution of imagery. There's something you've got to be very aware of here, though. You can take an image and you can so for example, you can take a low resolution image and generate an extremely good looking high resolution image, but the detail in the image isn't real. The detail in the image has been provided by the model. And so it may work from the point of view of making the old imagery look more like the modern imagery. But to be fair, we tried some non-deep learning approaches to that visually looked like they were doing a good job, and they didn't work. So you do have to be very careful about the difference between things that are being done for the sake of making something look good and for the point of view of being able to actually accurately delineate what's in an image. That you could, you may find that actually there's quite a big mismatch between those two things.
Fantastic. Look, we will come back to some of the other questions to those people directly. Thank you very much for coming along. Thank you very much, Brent, for a fantastic presentation. We will continue this afternoon, and Raphael and Hugh will be talking a little bit more about deep learning and how they've been applying that to predict landslide susceptibility. So if you've been fascinated by what Brent's told you about today, you can learn more about it this afternoon in our next session. We look forward to seeing you then, and thanks again for being with us today.